ADC fans do not automatically make a coordinated array.
Put the control sensor in the wrong place, or let several loops chase different targets, and the modules can speed up and slow down against each other while rack inlets still get hotter. Start with 5 project inputs: the IT load profile, acceptable rack inlet conditions, the real supply and return path, the pressure target, and the number of active modules.
These define what the array must do at peak and at part load. The physical fan module tells us geometry, inlet clearance, outlet arrangement, and service access.
It does not prove airflow, pressure, energy use, or redundancy. Those claims must come from the selected fan curves and the installed system test. The control loop needs one coherent demand. Measure temperature where the equipment receives air, and place the pressure sensor where it can actually see changes in IT airflow. Then let the master controller distribute a shared speed request and validate the result back at the racks. Send a deliberate command to every active module and compare requested speed with actual response. Small differences may be normal, but a persistent mismatch points to wiring, configuration, obstruction, or a module fault. Do not let independent trims fight unless the final controller design explicitly coordinates them. For this Longwell EC fan example, the specification lists a 230-volt supply, a 0 to 10-volt or PWM speed command, and an FG speed feedback output.
It does not list serial communication.
Current measurement, alarms, and richer telemetry therefore depend on the selected controller and project design. For the same air system, fan power changes approximately with the cube of speed, so modest speed reduction can reduce electrical input sharply. But that is a first check, not a guaranteed saving. System effects, air density, and fan efficiency still matter.
Trend measured fan power at the actual duty points.
The lowest possible command is not always the best command.
Stay inside an envelope where airflow is stable, the sensor retains authority, and every rack inlet remains acceptable.
Use the selected speed curves, not a generic minimum percentage. Build an evidence trail for each module: command, speed feedback, external current if provided, controller status, rack inlet temperature, and pressure trend. Available points vary by fan and controller, so define them before procurement.
When one module is isolated, the array has a new operating point.
Recalculate the remaining module speed and current, confirm control pressure, and inspect the worst rack inlet.
Only after every limit passes should the design be described as N+1.
Tune sensor filtering, deadband, ramp limits, integral time, restart order, and fault timeout to the dynamics of the real room. Then trend the response. A smooth graph is useful only when the inlet conditions are also safe. Before handover, replay 25, 50, 75, and 100% load, then isolate one module and verify recovery.
Record rack inlets, pressure, speed, and electrical power. Designing an EC fan array?
Send Longwell the rack load profile, airflow path, pressure target, array layout, selected curves, control interface, and one module off-duty point.